So if we pick up where we left off, we're talking about moments, and we talked about some moments in two dimensions. I just need to know the force times the distance for each of those forces. Now, later, we will talk about finding a moment vector, which is going to be based off of taking the force vector and performing an operation we call the cross product of the force and a position vector, a vector pointing to wherever we're taking our moment about. This position vector points from that point out to a line of or to any point on the line of action of the force vector, and that will tell us the three-dimensional components of the moment vector. But again, if we're dealing only in 2D, the force and the distance are both in the xy plane, and the moment vector has to be perpendicular to both. That is, that the cross product will result in a perpendicular vector to both f and d. If I'm in two dimensions, the only way that can happen is if the moment vector is in the positive or negative x direction. And that's what the clockwise and counterclockwise is telling us. Is it in the positive z direction or the negative z direction? So in two dimensions, we don't have to worry about the cross product. And I always like to try to start initially talking about two-dimensional moments, and then we'll come back and talk about three-dimensional moments, which means we are going to have to talk about the cross product. But let's not do that quite yet. Let's look at some examples with some 2D moments, and we'll go from there, okay? So, if we do that, if we look at some examples involving only 2D moments, and then we can start really working some some two-dimensional equilibrium problems. L6, page 4 of something. Got an example here. This is one of the more simple examples. A lot of times you'll find very simple examples like this in the text. I think this is something like 4, 8, or somewhere in that range. We draw here an xy plane where it's mostly here in the positive x, negative y quadrant. And we'll say that we've got a force down here at, we'll say, point A, and point A is 2 meters in the positive x direction and 5 meters down in the negative y direction. This is point A. And point A has a force applied to it of 400 newtons, and I've drawn the angle very poorly here. It's only supposed to be 30 degrees, and I feel like I've drawn it much more so than that. I apologize, I was off the screen there. Point B is up here along the x-axis at a distance of 6 meters from the origin. And again, it's just on the x-axis, so no y value to this one. This force is described by a similar triangle. This one is 260 newtons. And the similar triangle is a 5 in the horizontal, 12 in the vertical. That means 13 is the hypotenuse. 5, if you take 5 squared plus 12 squared and take the square root, you're going to get 13. So this is a 5, 12, 13 triangle where 5 is horizontal, 12 is vertical. And the magnitude of that force is 260 newtons. And what we want to do is we want to find the moment and what they call the directional sense of the moment applied to the origin. And what they mean by directional sense, a lot of texts will ask it in this way, and what they mean by directional sense is they simply mean, is it clockwise or counterclockwise? Right? So, what do we do here? Well, what you can do is you can say, well, how far is it from the origin to this point right here, to this line of action? Right? You could find this D to A basically, if you like, and you could do that. I personally don't care to do that. This is my preference, and in the text they talk about doing this. If you take a look at point A out here, so what I'm going to do is I'm going to draw this with the forces resolved. And I think you'll see why this is a little bit easier. So if I draw this with the forces resolved, point A is down here at, again, 2 on the x, 2 meters on the x, and 5 meters down here in the negative y direction. That's point A. And if I resolve this force, this is in the x direction. The x direction is adjacent to this 30 degrees. This is 400 newtons times the cosine of 30 degrees. That's the x component of that force. The y component is 400 newtons times the sine of 30 degrees. And then out here at 6 meters from the origin, you've got the y component of this force. That's the y component is based, if you look back up here, is based off the 12. And again, the hypotenuse of a 512 triangle is 13. So this is 12 over 13 is the vertical component. Let's just rewrite that. 12 over 13, because again, the 12 is the vertical half. The hypotenuse is 13. So basically we're saying, what is the sine of this angle? The sine of this angle is 12 over 13, opposite over hypotenuse. 12 over 13, 260 newtons. And then in the x direction, the x component of this force is 5 over 13 times 260 newtons. So, and again, we're trying to find the moment about the origin. So what I can do is I can write an equation. I can say if I sum the moments, all of the moments, I add up all the moments applied to the origin. And again, I'm going to call counterclockwise positive. Just that's the sign convention we will normally use. So if I try to find the moments about the origin here, what are we going to do? Well, let's go through each of these forces. So I've got this, if I start with this x component here, again, if you put your pin on your point of rotation, the origin, and you push your paper in the direction of that force, notice what happens when I push it. I get a counterclockwise rotation from this x component. So that is 400 newtons times the cosine of 30. That is the magnitude of that force. And that is the line of action for that force is 5 meters from the origin. Now, I'm not worried about the sine of this 5 meters. That sine is already taken care of in the fact that this is causing a counterclockwise rotation. That's the only sign I need to worry about. Is it counterclockwise or is it clockwise? That's going to determine whether it's positive or negative. Otherwise, I don't care about the signs of the force, the direction of the force, or the sign of the distance. It's all about, is it causing a counterclockwise rotation, which this one is. And then if we look at this one here, right? So if let's look at this y component. So if I push my paper in the direction of that force, notice that's causing this counterclockwise rotation. So again, that's also positive. So this is plus 400 newtons times the sine of 30 degrees. That's the magnitude of the force. I need to multiply that by the moment arm. Well, the moment arm, if you take this force right here and see, well, its line of action is 2 meters. Right? Basically, it's a y direction force, so I'm looking for its x distance. It is 2 meters. The line of action for that force is 2 meters from the origin. Now, if I look at this one here, or if I look at this component here, notice the line of action for this force goes to the origin. So I don't have to worry about that force. This other one, this y component, so if I push my paper in the direction of that force, when I hold my point of rotation constant right there with my pencil, or my pen in this case, notice I'm also getting a positive or a counterclockwise rotation. That is 12/13 times 260 newtons. That's the magnitude of the force. And this is, so it's a y direction force. That's 6 meters from the origin. Hazel's barking at something. That is 6 meters from the origin. So again, this is a y direction force. It's an x direction distance. Y force, x distance. X force, y distance. If you've resolved your forces into xy components, then that rule will pretty well hold solid. Let me see if I can figure out what she's barking at. I'm going to pause. My wife had moved something in the house, and Hazel decided she needed to bark at it. I apologize. All right, so we've talked about, hopefully, I've tried to give you a handful of different ways to figure out the direction of these different forces. Now, again, if we add in this x direction component, that's 5/13, 260 newtons, but it has a 0 distance to the origin because its line of action passes through the origin. So we don't have to add it. It ends up being 0. But all these others cause a counterclockwise rotation. Therefore, they're all getting added. I'll let you pause here, find the value, add these up. I have written here in my notes, if you're getting something different, tell me, 3.57 kilonewtons meters, and that is, of course, clockwise. You don't have to draw this. If you've made it clear over here, you wouldn't have to draw it there. But let me know what questions you have. I think I'm going to stop there for the night. I've got one more example will work. I'll post that video, I think, tomorrow. It's getting pretty late here. But this should get you started into your Chapter 4 problems at this point. All right. See you guys next time.